What's up guys, this is LeetCode 112, path sum. Given a binary tree and a sum, determine if the tree has a root to leaf path such that adding up all the values along the path equals the given sum. A leaf is a node with no children, given the below binary tree and sum equals to 22. Return true as there exists a root to leaf path, which sum is 22. Okay, so again, a tree problem where we have to iterate through this tree to find the answer. So here we have just to return true or false if a path that the sum of the nodes is equals to a number. So we have to iterate through all the paths. So to discover the end of a path, we have to check if the current node is a leaf or not. And yeah, if we discover that the current node is a leaf, we have to check if the path or the sum of all the previous nodes plus the sum of the current node is equals to the number that we are looking for. If this is true, we can return true. Otherwise, we can continue iterating through the other paths. We can do this using recursion. I think using recursion will be a pretty small solution, but we can also use an iterative solution with a stack. So yeah, we can solve this exercise using both approach, but I will start using the recursive approach first, and after that we can solve it using the iterative approach using a stack. So let's see how this works writing some code. Let's start by checking if the input is valid. So if root is null, we can return false. This is our base case of the recursive call. So we can also check now, as I said before, if we are in a leaf node. So if root.left is null and root.right is null. If both of these validations is true, means that we are in a leaf node, and if we are in a leaf node, we also have to check if the sum of the previous nodes plus the value of the current node is equals to sum. We can do this by checking if root the vol is actually, let me see, how can we do that? We can do that in a different way. We can check if sum minus root.vol is equals to 0, and if that's true, we can return true. And you understand right now, because if that's not true, we have to continue iterating through the tree, and to do that, we will use the recursive calls. So we can check if has path sum of root.left. And here is what I was saying, because we are gonna pass to this recursive call the subtraction of sum minus the current value of the current node. So we can do that by sum minus root.vol. And we also have to check this for the right side of the tree. So has path sum root dot right, and the same root minus root dot vol, sum minus root dot vol. I think if we do not have any typo, this is the recursive approach. Let's try to run the code. Let's try to hit submit. Yeah, that's it for the recursive approach. Time complexity here is, let's check here, is big O of n, where n is the number of nodes in this tree, because in the worst case, we have to iterate through all the nodes into this tree. And the memory complexity here is big O of h, where h is the height of the tree, because we will check for all the paths of this tree. So in a recursive approach, we will have the calls in the stack. We will allocate stack memory to the recursive calls. So that's it for the recursive approach. Let's try to write the iterative one. So the iterative one, as I said before, we will use a stack data structure. So let's declare it. And here we will use a stack of tuple. And our tuple will contain a tree node and an integer, because as we need a stack to do our iteration through the tree, we also need an integer to store the sum of the previous nodes until now. So we need the tree node and an integer. We have first to push the root node and also the sum of the previous nodes. And as we are in the root node, the sum of the previous nodes is 0. We have to iterate through the stack while the stack contains items. Okay, so here we can start by popping the top item on the stack. So we can do that by, let me see, the cur is equals to stack dot pop. And we can also declare some variables to make our work easier. So the current node is the cur.item1, and the path sun is the item2. Okay, so now we can start by checking. Yes, we will do the same checking we did before in the recursive approach. So we can check if the current node is a leaf node. So if the current node, if the node.left is null and node.right is also null, and if both these checkings return me true, it means that we are in a leaf node, and we have to check if the path sum is equals to the sum. So we can do that by path sum plus node.vol is equals to sum. If that's true, we can return true. Otherwise, we can add the left side of the tree and the right side of the tree into the stack. So let's first check if node.right is not null, because if it's not, we will push it into the stack. So root.node.right and the sum of the paths plus node.vol. And we also have to do this for the left side of the tree. So node.left, node.left, and the same sum here with path sum plus node.vol. If we get out of this iteration, means that we do not execute this line, and means that we did not find the path sum into this tree. So we have to return false. And if we do not have any typo here, I think that's the solution. Let's try to run the code. Okay, let's try to hit submit. And that's it. So time complexity for this solution is the same as the recursive one, is big O of n, where n is the number of nodes into these three. And the memory complexity here is also the same as the recursive approach, because here we are using the stack. We are allocating memory here with the stack, and we will use the stack to, let me see, to allocate the longest path into these three. Yes, so that's it. So memory complexity is big O of n. The memory complexity is big O of h, where h is the height of the tree. So that's it, guys. Thanks for watching.